Squaric acid is an electrophilic species that can readily react with nucleophiles to make squarane dyes. These dyes have an electron-rich donor on one end, a squarane bridge, and an electron-deficient acceptor on the other end. Their general resonance forms can be seen in Figure 1. This extended conjugation results in strong absorption and emission in the visible region of the electromagnetic spectrum, and due to the mobility of electrons, the opportunity for charge transfer arises. Due to these properties, squarane dyes can be used in dye-sensitized solar cells, biological imaging, and chemical sensing. In this research, we used a series of indole and aniline-based nucleophiles to examine the effects of different donors on the optical and electrochemical properties of these dyes. The structures of these target electron-rich molecules can be seen in Figure 2. The synthesis of these dyes, summarized in Figure 3, included creating a donor. To create donors, we have alkylated indole with ethyl bromide and aniline with ethyl hexyl bromide. We have done condensation reactions with squaric acid under reflux in toluene and butanol using indole, ethyl indole, and ethyl hexyl aniline to create 3 dyes. Cyclic voltammetry was performed to determine the ground state oxidation potentials of the dyes. These potentials can be used to measure the energy of a dye's highest energy electron in the ground state. Using absorbance data, we also calculated the dye's oxidation potential after it has absorbed a photon. The oxidation potentials of NKEC1 and ER2 were determined to be 0.934 volts and 1.214 volts respectively versus the normal hydrogen electrode. Excited state oxidation potentials for NKEC1 and ER2 were calculated at negative 0.886 and negative 0.896 volts versus NHE. The dyes were examined with UV-vis absorbance and emission spectroscopy. NKEC1 was the most redshifted dye with a maximum absorption wavelength of 648 nanometers. Lambda onsets were calculated with a tangent line pointed down the absorbance curve on the low energy side. The optical band gap was calculated using lambda onset and used to determine the energy of the excited state oxidation potentials. Future work on this project includes the determination of the molar absorptivity, excited state lifetimes, and emission quantum yields, as well as investigating the pH dependency of visible light absorbance of ER1 and computational studies to determine the molecular orbital distributions.